All right, so today what we're going to be looking at is, again, compound interest. The last time when we were working with compound interest, again, here's our formula here. 1 plus r to the power of n. All right, and so what we did last time out is we solved for A and P. We did that when the annual interest rate was just compounded annually, which made it a lot easier. But then in the last class that we did, we looked at finding out using compound interest when we were compounding at different compounding periods. So monthly, weekly, daily, quarterly, what's the last one? Semi-annually. All right, now, we always solve for A and P. We always knew R and N. So now what we're going to be looking at today is solving for N. Solving for N. So because that's an exponent, this comes back to our last unit of solving for exponential equations. So just a little bit of preview. Look at something like this. I got 1,325 is equal to 4 to the power of x. And again, I want to solve for x. And so what we did again last unit was we took the log of both sides. All right, and again, that's because we're solving for an exponent, just like we're going to have to do here with n. All right, now the log of 1325, I can put that in my calculator, and I get 3.1222. All right, now again, the reason that we are using logs to solve for the exponents is because there's a log rule that now allows me to bring this x down to be a normal number. And so I can just rewrite that log of 4 to the power of x as x times log 4. Now, log of 4 actually is a number. So again, I can take the log of that number. Again, the log function takes a very big number, makes it a lot smaller. And so in this case, I take the log of 4, and I'm getting 0.66021. All right. Now, of course, all I have to do now is divide by my numerical coefficient, which is the number beside the x. It's multiplying the x here. So in this case, it's my 0.6021. Divide that on either side. All right, so those divide each other out. And so my x is going to be whatever, 3.12222 divided by 0.6021, and I'm getting, rounding to 2 decimal places here, I'm going to get 5.19 is our x value. So again, that's just a little bit of review of last unit when we looked at exponential equations. Again, we're going to need that today. And so I get to example number 1, where we're dealing now with compound interest. All right, so again, I'm going to write down my 4 variables. So I got my accumulated amount, my principal, my interest rate, and n is the number of payments or the number of times the interest is added. Could look payments as in the interest is paying you. All right, so example number 1 here, it says, how many years will it take $400 to grow to $1,000 if it is invested at a rate of 15% compounded annually? All right, so to break that down, what we're looking at is we're looking at $400 growing to 1,000. So 400 is our principal. A, our accumulated amount, that is 1,000. Our interest rate is 15%, and that is compounded annually, which means the only thing I have to do is take that 15%, convert it to a decimal, again, dividing by 100%, and I get 0.15. Again, don't have to do anything with that because this is the simpler one where it's compounded annually. But we are trying to figure out how many times the interest is added. All right, so which again will explain how that will tell us how long it will take. All right, now going to substitute in my values. So I have 1,000. My P is 400. Now in brackets, I have 1 plus my interest rate. Well, my interest rate there is 0.15, so I'm going to have 1.15 to the power of n. All right, now we can't take the log yet, and this is a situation we had before. I am going to solve for n, but I'm going to have to get rid of this 400 first. So I'm going to divide both sides by 400. And let's see, so those 400s divide each other out. 1,000 divided by 400, I believe it's 2.5. Let me check it out here. Yep, it is. And so now I get 2.5 is equal to 1.15 to the power of n. Now here's where we get in this situation, almost identical except for the numbers are different. We're going to have to take the log of both sides. There we go. And again, the log of 2.5, that's going to be a very small number. In fact, I'm going to get 0.3979. All right, and then again, I'm going to use my log rule here. I'm going to bring the n down in front. All right, so we've done that before. Again, I'm going to simplify this, so I'm going to take the log of 1.15, which is going to be a very small number. All right, so I do that. I take the log of 1.15, and I get, oh yeah, it's a real small number here. 0.0607. And just like I did over there in red, I'm going to have to divide by my numerical coefficient, which is that 0.0607. And I'm going to do to one side, got to do to the other. All right, so those divide each other out. Now I get the number of times the interest is added. That's what our n value is all about. I'm going to explain how we're going to find the time on that. All right, so I take my 0.3979 and divide it by the 0.0607, and I'm going to get n is 6.55 times the interest is added. So it's kind of a decimal. Now here's the thing, is that because our interest is being compounded annually, the n is telling me that's how many years it would take. And again, that's because my interest rate is an annual interest rate. And so it takes 6.55 years for $400 to grow to $1,000 at an interest rate of 15%. All right, let's try another one of those. Then we'll step it up a bit. So again, logs, something we've done before, but just in a different fashion. That's all. Just real life money and not just solving for some equation. All right, so we get to example number 2. Again, we're going to be looking at, what? There we go. Example 2, again, we're going to be looking at compound interest, so I might as well just write down my formula. Here we go. All right, so again, I'm going to have my, let's write them over here. 4 variables. And, well, given the fact that our title here is compound interest finding n, might as well put a question mark there already, right? All right, so example number 2 now. It says if $1,000 was borrowed at a rate of 14% compounded annually, how long would it take for the balance to become $23,000? All right, so again, filling in our variables here. We're borrowing $1,000, and at what point does the bill become $23,000? That's not good. So again, principal, we're borrowing $1,000, and unfortunately, we want to know how long would it take to accumulate to $23,000. What am I missing here? My interest rate. It says how long would it take for my interest rate is 14% compounded annually. Again, it's going to change the next couple of examples. So again, I'm going to convert that to a decimal by dividing by 100%, so I get 0.14. All right, so now I'm going to substitute in my values here. So I have a 23,000. Get rid of this. 23,000 is my accumulated amount. My principal is 1,000. I got 1 plus my interest rate in brackets, so I'm going to have 1.14. And again, to the power of n. All right, so here we go. Again, this is an exponential equation. Same thing, just looks at a different way. But again, I'm going to have to get rid of this 1,000 first, so I'm going to divide both sides by 1,000. All right, so that's divide each other out. Well, 23,000 divided by 1,000. I don't have to use a calculator for that. It's just going to be 23. And then over here now I have my 1.14 to the power of n. All right, now is that time, because we're solving for that exponent, we're going to take the log of both sides. So I'll take the log of 23, and I take the log of 1.14, to the power of n, of course. All right, log of 23. Let's see here. That's going to be 1 point something, I guess. And it is. It's going to be 1.3617. All right, and again, I'm going to use my log rule here. So the n is going to come down and be a normal number now. There we go. And so once again, well, I'm just writing down this side. I got my n. I take the log of that small number, that 1.14. So I know it's going to be a very, very small number. And I get 0.0569. All right. And then, of course, my last step, which is dividing by my numerical coefficient here. And let's see here. I take those two, divide them out. And so my n value is, whoa, oh, well, that's what I would expect, I guess, 23.93. And again, we're looking for units here. Because this was compounded annually, that means this is the number of times the interest is added. So in fact, this time is also in years. So it would take almost 24 years, thankfully, if you borrowed $1,000 to get to $23,000 if it was compounded annually. Now, we're going to switch it up here. All right, so we're going to look at our other compounding periods, not just annual. So we'll mix it up here. But again, we're going to find n. We're going to end up using logs. All right, so the next example, well, I know, again, we're going to be using compound interest. So example 3, let's write our formula down. Oops, not I, R, oops, there we go. And I get my variables over here. All right, so I'm just getting ready before I read the question. Here we go. Borrowing again. If you borrow $100 off a friend who charges you 13% compounded monthly, yikes, how long will it take in years before you owe them $1 million? Yikes. All right, so let's see here. So you borrow $100 off a friend. So I'll put $100 in here. And I want to know how long it's going to take before you owe them, interest rate, nice friend, $1 million. So that's your accumulated amount, $1 million. All right. Now the interest rate. The interest rate is 13%, but it is compounded monthly. So first off, I switch the percent to a decimal, so I got 0.13. But because we're compounding monthly, I got to divide it into 12 equal parts. So I'm going to take that 0.13, divide it by 12, and I end up with, well, it's even going to be a smaller decimal. I'm going to get 0.0108. All right, so 0.0108 there for the interest rate. Again, and we don't know. So again, just with other compounding periods, setting it up is a little bit different. All right, now substituting in. So my accumulated amount, I want to know when my friend would owe me, or when I would owe my friend $1 million. Might not be my friend after that. Principal, I'm borrowing $100 off them. In brackets, we have 1 plus the interest rate, so I'm going to have 1.0108. And of course, we do not know n. All right. So just as we did before, I'm going to get rid of that 100 first by dividing on both sides. All right, so those 100s are gone. Now, if I take a million divided by 100, I think I just knock off 2 zeros here. And so I end up with 10,000. All all right, is equal to 1.0108 to the power of n. All right, now we've been at this spot 3 times now. I'm going to take the log of both sides. All right, so take the log of 10,000. I'm going to take the log of 1.08 to the power of n. Now the log of 10,000. Again, the log function, all it does is takes a number and converts it to a power with a base of 10. So I know 10 to the power of 4 is 10,000. So I bet you I plug in here log of 10,000, and of course it's 4. So that's what the log function's all about. But again, you can just pump in log of 10,000. Using my log rule here to bring the n down to be a normal number. All right, and again, I can take the log of that very small number. And that is going to be a huge decimal here. So I end up with, small, 0.0047. All right, now, again, I'm going to divide by my numerical coefficient, which is at 0.0047. Whoa. 0.0047. All right, those divide each other out, and now I get my n value, which is going to be 4 divided by that 0.0047. And my n value, we get, let's see here, 851. Now, here's the key. Now, it is crazy that I could borrow $100 off somebody and then owe them $1 million. But it is not going to take 851 years. This interest was compounded monthly. So that means my n value is talking about months. So if I wanted to know how many years it's going to take, I take my 851 and I divide it into 12, divided by 12, just see how many years it's going to take. And if I do that, it's going to take, now it is going to be a long time, 70.91 years. So I guess at your age, at 16, 17 years old, you borrow $100 off somebody, you guys might still be alive. Me, I don't have to worry about it. I'm not going to be around 71 years, I don't think anyways. All right, so that's how long it would take. So that's a little bit different because, again, the compounding period was different than annual. All right, I'm going to do one more of those. All right, so let's see here. Example number 4. Again, we got our compound interest formula. There's our variables over here. All right, let's see. Example number 4 now. Find how long it will take in years. So we got to convert everything in years at the end here. For $500 to amount to $7,500 at 7.5% compounded semi-annually. Wow, I got some typos going on there. All right, so that should be it. All right, so find out how long in years it will take $500 to amount to $7,500 at 7.5% compounded semi-annually. All right, so here we go. So again, we're taking $500. All right, now I want to know how long it's going to take to accumulate to $7,500. All right, and the interest rate is 7.5% semi-annually. All right, so first off, I'm going to take that 7.5% and convert it to a decimal, again, dividing by 100%. Now it's semi-annually, which means twice a year. So I have to take that interest rate and cut it in half, so it's 2 parts. All right, so I take that 0.075, I divide it by 2. I'm going to get 0.30375. All right, so that's that interest rate. That's my semi-annual interest rate, because again, it's twice a year, cut it into half. And once again, we are trying to find out. All right, so now, once again, I'm going to substitute my values in. And see here. So I have 500 is my principal, my interest rate plus 1. So I have 1.0375 to the power of n. All right, so again, like I've done before, I'm going to get rid of this 500. Divide each side by 500. So those divide each other out. I take 7,500 and I divide it by 500. And I get, 15. Yeah, that makes sense. 15. All right, and now I have my power here. All right, and just as I've done before, I'm going to take the log of both sides. So I take the log of 15 here, and I'm going to take the log. I'm going to skip a step here. I'm going to take a log of this, but again, I'm going to use my log rule. So essentially, it's just going to bring my n down in front. Might as well skip a step there. All right, now I'll take the log of 15 and the log of 1.0375. So the log of 15 is 1.17, and what else we got here? 6. All right. And then again, I'm going to take the log of that very small number, so I know it's going to be 0 point something. And it's 0.159. All right. Again, I'm going to have to divide by my numerical coefficient here. So let's divide by my 0.0159. Go, they're gone. And let's see here, our n value. I take my 1.176, divide it by my 0.0159, and I end up with 73.96. All right, so what is that? Does it take it roughly 74 years? No, it doesn't, because again, our interest rate was semi-annual. So what it's telling us, it would take 73.96 half years. And so to convert it to years, so these are halves of years, I'm going to divide it by 2. And that will give me how many years this will take. All right, because there's semi-annually twice a year, and it looks like it's going to be 36.98 years for that to happen. All right, so again, we're going back to our last unit and applying it in a financial application where we're using that to find our end value, which tells you, number one, how many times the interest is added, but at the same time, it's really telling you how long it's going to take. All right, so we did that both compounded annually. That's where you don't have to mess around with the final answer at all. It's always going to be in years. But then when you have other compounding periods, you need to make the adjustment both at the beginning with the interest rate like we did before, and at the end when you're actually converting it back into years.